Welcome to Spring LIB.
We are given the overall cell reaction for a hydrogen-oxygen fuel cell, and in part A, we want to determine what the standard cell potential is, as well as the change in Gibbs free energy at standard conditions. We can look and see that these are the two half reactions from the standard reduction potentials table that are combined together in order to produce the overall given reaction in the problem statement. We see that if we multiply the top equation by 2, then we cancel out 4 electrons on each side, as well as 4 H plus ions on each side. And now we can clearly see that we are left with the overall reaction that we are given of H2 gas plus O2 gas going to 2H2O liquid. And we see that the standard cell potential comes out to 1.23 volts. And that's one of the quantities that we wanted to determine in part A. And we can see and verify that we get that same value if we use the equilibrium constant K that we are given in the problem statement, in case we couldn't come up with these two half reactions. So we know that from the Nernst equation, when we are at equilibrium, the cell potential is 0. And if we are solving for the standard cell potential, then we do 0.0591 divided by those 4 moles of electrons times the log of K, where K is equal to the given value of 1.28 times 10 to the power of 83. And now if we isolate this equation to solve for that standard cell potential, we see that it does indeed come out to that same value that we just found of 1.23 volts. So that is the answer for the standard cell potential of this fuel cell. And now we can solve for the change in Gibbs free energy at standard conditions, which we know is just negative NFE at standard conditions. N is again equal to 4 moles of electrons. F is Faraday's constant, which is 96,485 coulombs per mole of electrons. And the standard cell potential is again 1.23 volts or joules per coulomb. When we calculate that out, we are left with energy units of joules, and if we divide by 1,000, we can get it in units of kilojoules, and we find that delta G at standard conditions for this hydrogen-oxygen fuel cell comes out to about negative 475 kilojoules. And now in part B, we want to predict what the signs are for delta H and delta S at standard conditions. Well, we just found a value for delta G at standard conditions, and we know that the equation that relates those 3 variables is delta G at standard conditions is equal to delta H at standard conditions minus T delta S at standard conditions. Well, we know from part A that we calculated a value of delta G at standard conditions to be negative, so we know that this has to be negative. We know that temperature has to be positive, since we are in absolute temperature scales of Kelvin to cancel off units of joules per Kelvin for the change in entropy delta S. And we know that Kelvin can only have positive units, it cannot be negative. So when we look at the overall reaction and first consider delta S, we see that we are going from 3 total gas molecules on the reactant side to 0 gas molecules on the product side. And we know that in order to predict the change in entropy, delta S, we know that is equal to the amount of disorder in the system. And we know that liquids are more ordered than gases. And so as we move from that initial state where we have 3 gas molecules going to a final state of no gas molecules, we become more ordered and therefore decrease the entropy. And so we can say that when we subtract that initial state from the final state, that delta S would come out to a negative value. So we know that delta S is negative based on that intuition. And now when we multiply a positive and negative value together, that comes out to a negative value, and we are subtracting that negative value, so we are adding it. So the only way that we can get a negative value of delta G is to have a negative value of delta H that is large enough to be more negative than whatever this overall positive term comes out to be. So based on that reasoning, we know that delta H at standard conditions and delta S at standard conditions are both negative, less than 0. And now in part C, we want to determine, as we increase the temperature, do we increase or decrease the maximum amount of work that we can obtain from the fuel cell? Well, again, if we consider delta G equals delta H standard conditions minus T delta S, and we know that the maximum obtainable work is equal to the negative of delta G, and we are increasing the temperature. Only when we increase that temperature and multiply it by a negative value for delta S, as we continue to increase that temperature, this term will become large enough that when we subtract it, we are again adding a positive value because delta S is negative. And so those negative terms cancel off, and due to a large temperature, a large positive temperature, as we increase the temperature, then that becomes a more and more positive term to the extent where it surpasses the negative magnitude of delta H, so that delta G becomes more positive. And as delta G becomes more positive, based on this relationship, the maximum obtainable work will decrease by becoming more negative. So therefore, as we increase the temperature, the maximum obtainable work that we can achieve decreases, because as we increase that temperature, we increase delta G and therefore decrease W max.